Jai Hind everyone. Once again, this is Jyoti Sharma giving you a lecture series on the topic electrical machines, which is the unit 4 of the subject Basic Electrical Engineering, having the subject code of KEE 101 according to AKTU. Coming to the lecture first of this unit, electrical machines, we'll be seeing certain contents that will be having EMEC process, that is electromechanical energy conversion process, DC machine construction, types of armature windings, working principle of DC generator, and EMF equation of DC generator and certain numericals on it. Now coming to the very first content topic, that is energy conversion process in machines. We have just discussed that the energy conversion process in the electrical machines are basically the electromechanical energy conversion process, right? So what is this electromechanical energy conversion process? As the name is suggesting, it is the conversion from electrical to mechanical, or the conversion from mechanical to electrical, as it is. This is a machine, right? So it needs to have the conversion of energy, right? Likewise, a transformer, we never used to call a transformer as a machine, we used to call it as a device, because it transforms the voltage level or the current level, keeping the frequency same, and it is a static device because it is not transforming any kind of energy to any other kind of energy. But electrical machines, right, these are the devices which transforms any one form of energy to another. And when I say electrical machines, specifically it is transforming an electrical energy into mechanical or mechanical energy into electrical. So as we say, an electromagnetic machine is the one that links an electrical energy system to another, basically mechanical energy system, by providing a reversible means of energy flow via magnetic field, right? So the magnetic field is therefore the coupling between the two systems and is the mutual link for the electromechanical energy conversion, as it can be seen from the diagram, right? So it is an electrical system I am having, it may be an input or output system. Similarly, then the coupling medium, this coupling medium is nothing but either the magnetic field or the electric field. And then the mechanical system, once again it can be an input and output depending upon which kind of machine is that, right? Now which kind of machine means, when I say it is converting an electrical input, the input being given to the machine is electrical and it is converting that into mechanical, then which kind of machine is this? Electrical input and the output is mechanical, that is a motor. Whereas if the input is a mechanical and the output is electrical, we see that with the electrical generator, right? So the energy transferred from one system is temporarily stored in the magnetic field and then released to the other system. Now for motoring action, obviously the total electrical input, right? A motoring action, the input has to be electrical. So the total electrical input has to be equal to the mechanical energy output plus the total energy stored plus the total energy dissipated, right? Similarly, for a generator action, obviously now the input would be mechanical, output would be electrical plus, if you just see, the total mechanical input is equals to the electrical energy output plus the total energy stored plus the total energy dissipated, right? Now coming to the very first machine what we are going to study. Now if at all I broadly classify the kinds of electrical machines, right, broadly classify. So if at all I broadly classify the types of electrical machines, it can be either based upon the kind of input they are giving or the input they are taking, right? So that can be either AC or DC. So I may be having DC machines, I may be having AC machines. Once again, machine is either a generator or a motor. We'll be studying that. But first we are concerning with, we'll be once again going with AC machines also, but we are starting with DC machine as it is easier to understand. The construction is very much similar with AC machines also. So the construction is also very easy to understand, right? So we are going to start with DC machines. So the main function of the DC generator, if at all I say, is to convert the mechanical power to the DC electrical power. Whereas a DC motor, it do the reverse. That means it converts the DC power to the mechanical power, right? What does an AC motor do? Right? An AC motor is frequently used in industrial applications for altering the electrical energy to mechanical energy. However, a DC motor is applicable where good speed regulation and ample range of speeds are necessary, right? Now, coming to the construction of DC machine, how does the DC machine is being constructed? What are its various parts? So, the construction of the DC machine can be done using some of the essential parts like the yoke, pole core, pole shoe, pole coil, field coil, armature, and the armature again consists of armature core, armature winding, or I may say conductors, commutator, the very important part of a DC machine, that is commutator, brushes and bearings, right? As it can be seen in the diagram here, if at all I say, I'll be starting with the outermost covering. The outermost covering of the DC machine is nothing but the frame or the yoke, right? We'll be discussing their individual parts also, what are their functions also. So this is the yoke. To the yoke we can see the magnetic system is being attached, or the field system is being attached, right? What is this field system, right? It is responsible for the production of the field, right? So what it is having? It is having the field poles. North, south, it can be depending upon the number of poles. So it is the field poles. Obviously, these are electromagnets. These are not permanent magnets. So these needs to be magnetized. That means these would be magnetized while they are having certain current. For that, I need to provide certain windings, right? So the windings, it can be seen over here, this portion, the portion it can be seen around the poles, right? This portion, it shows the field winding, right? These are the portion which shows the field winding around the pole. Then inside to it, it can be seen I'm having the armature, right? Once again, armature will be having core, it will be having the armature conductors, individual will be taking them. First, to start with the yoke part, right? The outermost part. So the another name of the yoke is frame. The main function of the yoke is, in the machine, it used to offer the mechanical support intended for the poles and protects the entire machine from the outside atmospheric environment like atmosphere, dust, etc. The material used in the yoke are designed with the cast iron, cast steel, otherwise it can be a rolled steel as well. It can be seen in the figure over here, right? So this outermost portion, what can be seen over here, this is forming the yoke. Now coming to the second part, that is pole and pole core, right? Now the pole of the DC machine, what is that? It is nothing but an electromagnet, and the field winding is the winding among these poles. Whenever the field winding is just energized, then the pole gives this magnetic flux which is required for the production of the EMF. The material used for this are generally cast steel, cast iron. It can be built with the annealed steel laminations. And why the laminations are being done? Obviously to reduce the power drop because of the eddy currents. Then the pole will be having an extended portion which is being called as pole shoe. What it can be seen in this figure, right? These are the poles. These are the poles, the magnetic poles, right? The pole shoe in the DC machine, it is an extensive part as well as to enlarge the region of the pole. And what is being enlarged? Because of this region, the flux can be spread out within the air gap, as well as the extra flux can be passed through the space towards the armature, so that the material used for this to build this pole shoe is generally the cast iron, or it can be the cast steel, right? Also the annealed steel laminations are once again used to reduce the eddy current losses, right? Now the windings which are being wound on these poles gives us the field winding. It can be seen over here, the windings, the field windings, it was being shown. This is the field magnet and the windings being shown in this, right? The portion here that shows the field winding. So in this, the windings are wounded in the region of the pole core and named as the field coil. Whenever the current is supplied through the field winding, then this electromagnetizes the poles, right, by which the poles are being created, north, south, right, which generate the required flux. So the material used for the field winding generally is copper, we know that. Now coming to the another important part, that is armature, right, the armature core, the very first important portion of the armature, that is armature core. It includes a huge number of slots within its edge. So the armature conductor is located in these slots. It may be provided with air ducts for the axial airflow for cooling purpose. The armature is keyed to the shaft. It provides the low reluctance path towards the flux generated with the field winding. The material used in this core are, once again, it has to be a highly permeable material and it has to have a low reluctance, likewise iron or cast steel, right. We want to have a high permeable material to reduce the hysteresis losses. We need to have the laminations to reduce the eddy current losses, right. So it can be seen over here, this is the armature core, complete portion. It used to have these slots. These are the slots which can be seen over here. And in these slots, we'll be having the conductors, that is the armature windings being wound, right. So in this, it can be seen here. Now I'm having the armature, now the windings are being wound in this, right. So the armature winding can be formed by interconnecting the armature conductor. Whenever an armature winding is turned with the help of the prime mover, then the voltage as well as the magnetic flux that get induced within it, right. So this winding is lead to an external or exterior circuit, right. So the material used for this windings are conducting material like copper. Once again, whenever the windings are there, it has to be either the copper or the aluminum which are being used for the windings. So the armature windings can be wound by one of the two methods. It can be either lap wound, that means lap winding, or wave winding. We will be seeing what is the difference between the lap winding and a wave winding, right. Now comes a very important part of the DC machine. What is that? That is commutator. Now, what is the function of this commutator? It can be seen in this figure. That commutator, you can see here, these are the segments. This complete portion, this is nothing but a commutator, right. So the main function of the commutator in the DC machine is to collect the current from the armature conductor, as well as it supplies the current to the load using brushes. It also provides a unidirectional torque in case of DC motor, right. So the commutator can be built with a huge number of segments in the edge form of hard drawn copper. The segments in the commutator are protected from the thin mica layer. The number of segments is equal to the number of armature coils. Each segment is connected to an armature coil and the commutator is keyed to the shaft. That means commutator is that part of the DC machine which actually converts the internally developed AC into equivalent DC in case of generator, and it used to also provide a unidirectional torque if it is a DC motor. The last part what it can be seen is nothing but the brushes, which is these are nothing but the carbon brushes which are very much required for what is the function of the brushes. The brushes in the DC machine, they gather the current from the commutator and supply it to the exterior load or the external electrical load being connected. The brushes wear with time to inspect frequently, right. So the material used in the brushes are generally graphite, otherwise carbon, which is generally rectangular in form. So it can be seen from here. These are the carbon brushes which are being provided over here. Now coming to armature winding, when we were studying armature winding, so we just saw what is actually an armature winding, right? The armature that is completely slotted, it is circular in shape, it used to have slots on its periphery, and the number of slots is equals to the number of the commutator segments what we are having. Now in these slots, I need to have armature windings being wound so that the EMF can be induced in the armature. Now these conductors what I have placed in the slots, right? The fashion in which these armature conductors are connected, I used to call that as armature winding. So I can wound these armature conductors basically in two ways. What are those? The very first way is it can be either a lap wound armature or it can be a wave wound armature. Coming to the very first one, that is lap winding or lap wound armature. What used to happen in this? As the name is suggesting, the lap winding is the winding in which the successive coil overlaps each other. That's why it is named lap winding, because it doubles or laps back with its succeeding coils, right? In this winding, the finishing end of one coil is connected to one segment, commutator segment, and the starting end of the next coil situated under the same pole and connected with the same commutator segment. So here we can see in the picture also that the finishing end of the coil 1 and the starting end of coil 2 are both connected to the commutator segment 2 here. Both of these are connected to commutator segment 2 and both the coils are under the same pole also, right? Now, what is this wave winding now? As the name is suggesting, it is wave, it is progressive, it will never be lapping back, right? So the wave winding is another type of armature winding. In this winding, the end of one coil is connected to the starting of the other coil of the same polarity as that of the first coil. So in this type of winding, the coil A, the coil side say AB, that progress forward around the armature to another coil side and goes on successively passing through the north and south till it returns to the conductor A1, B1, right? A1, B1, lying under the same starting pole. So this winding forms a wave with this coil. That's why it is being named as wave winding, right? It is also being called as series winding because its coils are just connected in series, right? Now, what are the key differences between this lap winding and wave winding? So if you just see, in case of lap winding, the coil is lapped back to the succeeding coil, whereas in case of wave winding, the coil are connected in the wave shape. That is the very first difference. The second difference, in the lap winding, the end of the armature coil is connected to the adjacent armature segment, whereas in the wave winding, the end of the armature coil is placed in the commutator segment which is placed apart, right? A lap winding, third difference, in lap winding, the number of parallel paths is equal to the total number of poles of the coil. This is a very significant difference, right? That means in a lap winding, the third point, number of parallel paths which we just denoted with the letter A. In case of lap winding, this is equals to the number of poles of the DC machine, right? Whereas in case of wave winding, the number of parallel paths is always equals to 2, right? Let it be any number of poles, the number of parallel paths for the windings will always be equals to 2. So here, in this case, I'll be having more number of conductors being connected in series. Yes, because I'm having only 2 parallel paths. Say supposingly, if the motor or the generator is of 4 poles, right? So in that case, in case of lap wound generator, in that case the number of parallel paths would be equals to number of poles, that is 4. So I'll be having 4 parallel paths. So my conductors which are coming in series, say Z are the number of poles. Say if at all I say Z, capital Z, that gives me the total number of armature conductors. So how many conductors are coming in series for a lap wound generator? In that case, that will be Z by A, but A is equals to P. So Z by P. So I'll be having lesser number of conductors in series, whereas in case of wave wound, it will be Z by just 2. In let it be any number of poles, right? So in that case, I'll be having more conductors in series. More conductors in series means I'll be having a higher value of EMF being attained at the terminals. That can be seen in further portions. So coming for the fourth difference, so the lap winding is also called the parallel winding. It is forming laps because their coils are connected in parallels, whereas in case of wave windings, the coils are connected in series. Hence, it is also being called as series winding. Fifth difference, the EMF in the lap winding is less as compared to wave, right? For the very known reason that obviously in a lap winding, the number of connectors coming in series are less, whereas in wave, the number of connectors coming in series are more. So it will be having more EMF. Sixth difference, in lap winding, the number of brushes is equals to the number of parallel paths, whereas obviously the number of parallel paths, those many number of brushes needs to be required to collect the current and make it available to the external circuit. Whereas in case of wave winding, always, because the number of parallel paths is always equals to 2, so the number of brushes required is always equals to 2. Seventh difference, the efficiency of the lap winding is less as compared to the wave winding. And the eighth difference, the lap winding is used in the low voltage, high current machines, whereas in the wave winding it is used for high voltage and low current machines. It is very much obvious. Low voltage we have seen because the number of conductors coming in series are less, but the number of parallel paths are more. It means, right, the total or the collective current taken by the lap wound armature can be increased because the number of parallel paths are more, whereas in case of wave wound, as the number of parallel paths is only 2, so I am just restricted with the small current applications or low current application machines. So these are the key differences between the lap and the wave wound armature. Now coming to the working principle of DC generator. Now we are discriminating between a generator and a motor, right? Till now what we have studied, the complete construction, the types of armature winding, this is all same for DC generator or for a motor, right? But now coming for the working principle of a DC generator, it can be seen, it is very much similar to an AC generator, except the very one difference, that is commutator. Otherwise, as you have studied, you must have studied, all the students must have studied the AC generation in, I suppose, the second unit of the same subject, basic electrical engineering. The same concept is there, where the AC generation you have studied according to the Faraday's law of electromagnetic induction. When a conductor moves in a magnetic field, thereby cutting the magnetic flux lines, a dynamically induced EMF is produced in the conductor, right? Dynamically induced EMF. I suppose everybody knows this dynamically induced EMF. Basically, the two kind of EMFs can be, we can be having two kinds of induced EMF. What are those? The very first kind of induced EMF is statically induced EMF, right? What is the statically induced EMF? Another one is dynamically. As the name is suggesting, statically induced EMF is the induced EMF which has been induced because obviously I need to have a Faraday's law, I need to have a d phi by dt, then only the induced EMF would be there. But in this case, I don't have any rotating part. Where do I have this statically induced EMF? The best example, in my previous lecture, we have seen in transformer, we don't have any rotating part, right? It is a static device, but we are getting an induced EMF, right? Because of the alternating supply what you are giving, because of the alternating voltage you are giving, the current is also alternating, the flux is also alternating. Because of that, you used to have a statically induced EMF. Once again, the statically induced EMF can be of two types. In the transformer, both the EMFs were there. What was that? One is self-induced EMF, another one is mutual induced EMF, right? So we have seen in transformer, in the transformer primary, the statically induced EMF was the self-induced EMF, right? Whereas the EMF induced in the primary, that was the mutual induced EMF. That is the principle on which the transformer works. Coming to DC generator. We don't have a statically induced EMF over there. We have a rotating part, right? So, the EMF induced in a DC generator or a motor, that is nothing but a dynamically induced EMF, because this is the induced EMF what we are getting because of the electromagnetic induction. But because of what is electromagnetic induction, I need to have a rate of change of flux. It can be because of the rotation of the conductor with respect to the field, or it can be the rotation of the field with respect to the conductor, right? Either the two has to move. I need to have a relative motion between the two. The magnitude of the generated EMF can be given by the EMF equation of the DC generator, which we'll be just seeing. Now, if a closed path is provided to the moving conductor, then the generated EMF causes a current to flow in the circuit. Thus, in DC generators, when the armature is rotated with the help of the prime mover, right, it has to be rotated with the help of the prime mover, and the field windings are being excited because these are electromagnets, right? They may be permanent magnet, right? They may be the permanent magnets, but generally they are electromagnets. These needs to be excited. That's why we used to have the field windings. Then the EMF would be induced in these armature conductors. This induced EMF is taken via commutator brush arrangement. What is the function of commutator? We have seen that due to this method, the EMF induced in the armature winding would be of what nature? AC. What will be the magnitude? BLV sin theta. Induced EMF has to be BLV sin theta. What is this B? That is BLV sin theta. Magnetic flux density, the active length of the conductor, the velocity of the conductor at which it is moving, and sin theta, the angle it is making, right, with respect to the conductor plane. So, that will be the induced EMF, but the nature is alternating. Now, it is the work of the commutator that it converts this internally developed alternating voltage into DC, and now this DC is made available to the external circuit with the help of the brush arrangement, right, which are fixed. The direction of the current, in which direction the current has been induced, right, or the EMF has been induced. So, the direction of the current that can be determined by Fleming's right hand rule. What is Fleming's right hand rule? If we just remember, right, this rule states that if we stretch the thumb, index finger and the middle finger of our right hand perpendicular to each other, then the thumb indicates the direction of the motion of the conductor, right. The index finger that indicates the direction of the magnetic field, north to south or south to north, whatever, right. Generally, the direction of the field, that is always from north pole to south pole, and the middle finger that indicates the direction of the flow of the current through the conductor, which is unknown in case of DC generator and can be known using Fleming's right hand rule. Now, we have seen how the DC generator work. Now, the important thing is, what is the EMF that is being generated in the DC generator? The DC EMF that has been generated in the DC generator, right. So, to have that equation, we know that the working principle of the DC generator, that when conductor begins to cut the magnetic lines of forces, and therefore the EMF induced in the conductors according to the Faraday's law of electromagnetic induction, then the value of the induced EMF that depends upon the length of the conductor, the magnetic field strength and the speed at which the coil rotates. That is what you call it as BLV sin theta. Now, let us see the equation for the induced EMF, right. If at all I just let that phi is nothing but the flux per pole in Weber, right. And what is Z? Z, I have just told you, that is nothing but the total number of armature conductors on the complete periphery of the armature. N is the armature rotation in revolutions per minute. Obviously, the armature is rotated with the help of the prime mover, right, and N is the speed at which that armature is being rotated in RPM, revolutions per minute. P is obviously the number of poles of that particular DC machine or DC generator. A, it is the number of parallel paths in the armature winding, and we have just discussed that this number of parallel paths in armature, that is equals to P if it is lap wound, and it is equals to 2 if it is wave bound. Then E, if at all I say, is the EMF induced in any parallel path or generated EMF. Then according to the Faraday's law of electromagnetic induction, we know that the average EMF generated per conductor in a single conductor, that has to be d phi by dt, that is the flux cut by time taken. Now the flux cut per conductor in one revolution, that has to be flux multiplied by number of poles. Similarly, the number of revolutions per minute, that is n by 60. So the time taken for one revolution, that is dt, that becomes 60 by n seconds, as n is the speed in revolutions per minute. So the time taken for one revolutions in seconds, that becomes 60 by n seconds. So the EMF generated per conductor in a single conductor, that becomes 5p divided by 60 by n. So that becomes 5pn by 60 volts. But do remember that once again, this is the EMF generated per conductor in a single conductor. So if at all I want to have the total EMF generated between the terminals, right? If given as E is equals to average EMF generated per conductor by the number of conductors in each parallel path. And how many conductors are coming in series in a single parallel path? That has to be Z by A. My total number of conductors are Z, number of parallel paths is equals to A. So that needs to be multiplied with my average EMF generated per conductor. So that becomes 5pn by 60 into Z by A. So the total induced EMF, that becomes 5pn by 60 Z into Z by A, where obviously A is equals to P for the lap winding and A is equals to 2 for wave winding. That is all for today. In the coming lectures, we are going to discuss the numericals for the EMF equation and what are the types of DC generators we are having. Thank you all.